Hello, it's me, Billy Younger again, and we're going to learn some more physics. This time I'm wanting to show you that the exponential raised to an I power could actually be used as a sinusoidal or cosine type function. In order to do that, I need to introduce you to Euler's formula. So I'm going to actually motivate Euler's formula. I'm sort of going to give you a proof. I'm not going to actually go through all the work, but you can see it from what will do. And from that, we'll get a nice compact version of Euler's formula. And then Euler's formula we can use to represent cosine and sine. And that, because cosine, for instance, cosine of kx minus omega t or sine of kx minus omega t is a plane wave. So we could actually use an exponential to represent a plane wave as well. So let me get started by turning on my document cam. So in order to do this, you need to be able to recall the Taylor series and more specifically the Maclaurin series. So the Taylor series basically said that f of x, any function, could be written as the summation from n equals 0 to infinity. And of course, it had some certain mathematical constraints, but those mathematical constraints are almost always satisfied by physical problems. So we almost never have to deal with it. But in fact, it would be equal to the nth derivative. That's why I'm putting it in little parentheses here. It's the nth derivative evaluated at a. So the function f of x, you take the nth derivative of it, and then you substitute a for x. And then you take x minus a, and you raise it to the n power and divide it by n factorial, where n factorial is, for instance, if n was 5, it'd be 5 times 4 times 3 times 1. If it was 7, it'd be 7 times 6 times 5 times 4 times 3 times 1. And we also define 0 factorial is defined to be 1, and we define 1 factorial is also defined to be 1. And we finally define f0 of x to just be f of x, okay? Now, in our case, we're actually going to do the Maclaurin series, and the Maclaurin series is the same thing except it's expansion about 0. So we're going to say f of x is equal to the summation from n equals 0 to infinity of f, nth derivative of f, that is, evaluated 0 times x to the n over n factorial. So what we have is three functions. I'm going to say f sub e of x is equal to e to the ix. I'm going to say f sub s of x is equal to sine of x. And I'm going to say that, let's skip 2 lines again, f sub c of x is going to equal cosine of x. And we're going to basically do a Maclaurin series expansion for these functions. And when I do them, we'll end up being able to just look at it and identify exactly what e to the I theta, which is really what we're looking for, e to the I theta equals question mark. And in fact, that's Euler's formula, is e to the I theta is equal to a result that we'll see in a second. So first off, I'm going to say f sub e of 0 is obviously e to the 0, which is just 1. I will say and that of course is also the same thing as f0, because remember f of f, the 0th derivative of s is just defined to be f of x. The first derivative of f, of course, would be I times e to the ix. So in this case, it's going to be I times e to the 0, which of course is just equal to I. And then fe second derivative evaluated at 0. I'm going to take the derivative of this, which is just I is just a constant, but I'm going to take the derivative of e to the ix. That's going to give me another I. So I'm going to get I squared e to the 0, which is just negative 1. I then take, say, the third derivative. And it turns out you can do this basically up to about the 4th or 5th derivative, and that really gets you far enough where you see the pattern. So the third derivative would be the derivative of I squared e to the ix, which becomes, of course, I cubed e to the 0. And of course, I cubed, two of them makes -1. And then the next one would be negative I. So that's going to be negative I. We do f IV, the fourth derivative, evaluated at 0. That's the derivative of I cubed times e to the ix. So I end up getting I to the fourth e to the 0. And that really is enough, because this turns out to be I to the fourth would be -1 times -1, which equals +1, which I think you can see is we're back to basically e to the 0 again. In other words, once I get to here, the next derivative I take is actually this derivative, in fact, is exactly equal to the 0th derivative. So the fifth derivative would be the same as the first derivative, and the sixth derivative would be the same as the second derivative, and so on and so forth. So the pattern is 1, I, -1, negative I, and then after negative I, we got the 1 again. So it should be ... Easy peasy. So now I've got all these values put in, and notice it's kind of nice because it turns out to be the 0th derivative is I to the 0 power, which is the same thing. The x will be raised to. The first derivative would be I to the 1 power, which is the same thing. The x is raised to. The second derivative is I squared, which is the same thing. X is raised to the power of I cubed is the third. I fourth is the fifth, so on and so forth. So we can actually make very good sense of that. Similarly, we can do the same thing. I'm going to go ahead and take a second and write out what e to the I x would be. So e to the ix, we can see clearly in the first case, hopefully, yes, I haven't written it too far down there. In the very first case, the f0, I got 1 over 1 over 0 factorial, because this is n equals 0. So 1 over 0 factorial times x to the 0. So that's just, in fact, 1. And then the next one would be the first derivative, which is I times, or I to the 1 power times x to the 1 power. So this would, in fact, be plus I times x over 1 factorial. And then the next one, of course, would be I squared, which is -1. So I'm going to write negative x squared over 2 factorial. And then I'm going to write, after that, I'm going to write the third one, which you can see the third one is going to be negative I. So I'll say negative I x cubed over 3 factorial. And then the next one, after negative I, we're back to 1 again. So this time it's going to be plus x to the 4th over 4 factorial minus ... That's pretty much it. And you can see what the pattern is. Obviously, the sign, it's going from, it's going through the same pattern where it'll be 1. The next one will be 1. Actually, no, excuse me, that one was 1. So the next one will be I times x to the 4th over x to the 5th, excuse me, over 5 factorial, then minus, so on and so forth. We can continue on to do the sign, and the 0th derivative of the sine of x evaluated at 0. The derivative, well, actually, the sine of 0 is actually equal to 1, is actually equal to 0. So the first derivative evaluated 0 is the derivative of sine, which is, of course, cosine. So I'm going to evaluate the cosine of 0. And, of course, the cosine of 0 is 1. So we've got that. Next is going to be f sub s of I. So that's the second order derivative evaluated at 0. In that case, we're going to get the derivative of cosine, which is negative sine of 0, which would be, of course, -1. We can again go to the f I, the third derivative evaluated at 0 of the sine function. And of course, this one was negative sine, so the derivative of sine is cosine. So this is going to give me a negative cosine evaluated at 0, which is going to be -1. And then f IV, the fourth order derivative, S, evaluated at 0, is going to be the derivative of negative cosine, which is negative times the derivative of cosine, which is negative sine. So it would be positive sine evaluated at 0, which equals 1. So we start back all over again. From that, you can put together that the sine of x is in fact equal to 0 plus x over 1 factorial plus 0 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus ... I think you can see the pattern, but basically what we're realizing is that the sine of x looks just like these terms, the odd terms, and in order for us to make it the same, we're basically just going to have to put an I in front of it. So this term looks like the first term, I times the sine of x, and this looks like I times the third term, or which is actually the second surviving term. When we do the same thing with cosine, we get FC 0 at 0. That's the function itself of cosine of 0, which is obviously equal to 1. FC 1, the first derivative, evaluated at 0, derivative cosine is sine. Sine of 0, of course, is equal to 0. We take the second derivative, evaluated at 0. Second derivative is derivative of sine, which is cosine. Oh, this one should have been negative sine. Sorry about that. Derivative of cosine is negative sine, but negative of 0 is still 0. The derivative of negative sine would be negative cosine, but that's negative cosine of 0, which is equal to negative 1. The F3 of cosine evaluated at 0 is going to be the derivative of negative cosine. The derivative of cosine is negative sine, so this will be positive sine evaluated at 0, which of course is 0 again. And you can see the pattern. In fact, it turns out that in the case of cosine, we have, for sine, notice we only had odd problems. For instance, we had x to the 1 over 1 factorial. Then we had minus x to the 3 over 3 factorial. Then we had plus x to the 5th over 5 factorial. Then we had minus x to the 7th over 7 factorial. Then we had plus x to the 9th over 9 factorial minus ... In this case, we're getting cosine of x, and cosine of x turns out to be 1 plus 0 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I'm cutting out the zeros now instead of actually putting them. Minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus ... You can see that fills in these spots. So if you look at this, this, and this, you can ultimately see that e to the I theta is actually equal to cosine theta plus I times the sine of theta. And in fact, if you want to go further, you can say that e to the negative I theta is equal to cosine theta minus I sine theta. Now, this is the real part of e to the I theta. This is the imaginary part. This is the real part. This is the imaginary part. If you take e to the I theta and add to it e to the negative I theta, what you get, of course, is e to the I theta would be cosine theta plus I sine theta. And then e to the negative I theta would be cosine theta minus I sine theta. So you end up getting 2 cosine theta. So you can see cosine theta is in fact just equal to e to the I theta plus e to the negative I theta over 2. And in fact, you can do a similar process. This time, instead of adding, you subtract them, and you would find that sine of theta is equal to e to the I theta minus e to the negative I theta. And this time you have to divide it by 2i. So all of this allows us to do cool things like if we want to talk about basically cosine of kx minus omega t, we can use that as e to the I kx minus omega t plus e to the negative I kx minus omega t over 2. Similarly, if we do the sine, we'd have to do a subtraction, and we do over 2i. But that is just a way we can get into trig functions, and sometimes it's a lot easier to work with exponential functions when you're doing certain proofs and identities than it is to work with trig functions. So that's it. That's a pretty exhaustive tale about how e to the I theta is defined via Euler's formula as cosine theta plus I sine theta. I hope that helps.